All right. Hello, everyone, and welcome to the civil seminar. So today, I'm very pleased to introduce Dr. Francis Zwiers, um, who is going to present some of his works and his team's work related to the engineering design for future climates, navigating a complex intersection of disciplines. So before I start, I should mention that I had the privilege of working with Dr. Zwiers as a postdoc and afterwards as a research scientist um, before 2017 for about 3 years. And I had one of the best periods of my research career was actually spent during that time, and I learned a lot from him. So as a quick background, Dr. Zwiers is the director of the Pacific Climate Impacts Consortium, or PCIC, at the University of Victoria. Prior to that, he was the chief of the Canadian Centre for Climate Modeling and Analysis, or CCCMA, which is also in Victoria and is actually very close to PCIC. And also he was the director of the Climate Research Division. And both of these are part of the Environment and Climate Change Canada. So his expertise is in the application of statistical methods to the analysis of the observations and simulations by the climate models. And his focus is on climate variability and change. Dr. Zwiers is a fellow of the Royal Society of Canada, the American Geophysical Union, and the American Meteorological Society. And he is a recipient of the Patterson Medal and President's Prize. He has also served as the Intergovernmental Panel on Climate Change as a coordinating lead author for the 4th assessment report, and is an elected member of the IPCC Bureau for the 5th assessment report. And with that said, please join me in welcoming Dr. Zwiers. Dr. Zwiers, the floor is yours. Thanks.
So thank you very much, Reza. It's an embarrassingly long introduction, but
it's actually quite short.
But it's a real pleasure to be able to speak to this impressively large group, and it's an honor for me to do so. So I'm going to share my screen now, if I can. So you should be.
Yes, we can see that.
Okay, so they're now. So it should now be in full screen mode.
Yeah.
Okay, and so here's the title page. And so what I'm going to do is talk about some work that we've done at PCIC that relates to the engineering community and what they might have to design for in the future. And at the same time, I'll try to entertain you by showing a series of photos that I've taken different places, mostly in Western Canada, but also some other places. Not quite so recently because travel isn't really possible, hasn't been possible for the last while. So as in terms of an outline, I'll describe work that we've done with the National Research Council on a climate resilience initiative, saying what our contributions have been. And then about 2/3 of the talk will be to discuss the questions that I've basically learned how to ask as a consequence of doing that work. And so I'll be asking those questions from the perspective of a climatologist and a statistician. My history is that I was initially trained as a statistician, and Reza had to suffer with that. So first, the climate-related buildings and core infrastructure. Core Public Infrastructure Initiative, which was an initiative of Infrastructure Canada. They provided funding to the NRC, and so we worked with the NRC under contract as part of that initiative. What you're seeing here is a bridge built in British Columbia in 1926. It's no longer used, but you can still go and visit it and walk on it. It's part of a park. It crosses the Fraser River, and when you stand on the middle of this bridge in June, it's a really impressive experience. There's something like 10,000 cubic meters per second of water flowing by underneath you. You just feel the bridge moving and responding to that water. So this was an NRC-led initiative to ensure that codes and other design tools are consider the impacts of climate change and extreme weather. As I mentioned, funding was from Infrastructure Canada, so it's a 5-year program beginning in 2016. There are a bunch of requirements for building and bridge codes that you might think about in terms of climate. So the current codes assume a stationary climate, but Canada's warming, and it's warming pretty rapidly at about double the rate of the global mean, and it will continue to do so in the foreseeable future. Certainly our climate is becoming warmer, and that has influences on things like snow loads and also extreme precipitation. So annual precipitation totals are projected to increase with a shift towards less snowfall and more rainfall. And the frequency of extreme events are being affected. So we've just experienced a very extreme flooding event in British Columbia that we've analyzed and have found some connection between human influence on the climate and the probability of occurrence of that event. But climatic loads need to account for changing climate, particularly future changes. So climatic loads that are used in engineering design. And they also need to be updated for the current climate. So those were 2 tasks that we were given. Some other requirements, current codes are based on, in Canada, are based on what's called a uniform hazard approach. And what that means is that climate load factors are fixed, and that fixed climatic load factors are used, I should say. So you might estimate what an extreme snow load is, and then multiply that number, or an extreme wind load, and then multiply that number by a fixed factor in order to account for uncertainty. And what that leads to is non-uniform levels of reliability across Canada, because uncertainty in these loads is different from place to place. And so the NRC wants to find a way of dealing with that. And the way to deal with that, one way to deal with that, is to adopt what's called a uniform risk engineering approach in Canada in building and bridge codes to yield more uniform reliability across the country. And what that implies is to replace a combination of a 50-year load, 50-year snow load, or 50-year wind load, for example, with a fixed load factor such as 1.4 or 1.5, with a load that corresponds to a longer, much longer return period, but used as a load factor of exactly 1. So you dispense with the load factors. You deal with the uncertainty entirely by asking about extreme events that are much rarer than the kinds of extreme events that are currently tabulated in the National Building Code of Canada. So some requirements, or some further requirements, have to do with what kind of reliability criteria you design for. So the ability of a structure to bear climatic loads is to a large extent determined at the time of design. So the loads that you use for today's climate might be too large for the future. In a warmer climate, for example, low temperature thermal loads or snow loads would be expected to decrease, or they might be too small. High temperature thermal loads or extreme rainfall might be expected to increase. And thus the instantaneous reliability of an ideal structure, so a structure that doesn't deteriorate for other reasons, will change in a complex and likely nonlinear way as the climate changes, because some loads increase, other loads decrease. And so the engineering community, I think, needs to think about how they would define reliability targets in such a non-stationary state. And so that's something that the initiative hasn't dealt with yet, but I think that the engineering community needs to think about. Okay, so first quickly about updating historical climate design data. This is a photo of a road that runs over permafrost in the Yukon that was built quite some time ago now, the Dempster Highway. So it relied on design data that was available at the time, its design. The current climatic design values are listed in the National Building Code of Canada and in CSA S6, which is the bridge code. And so we worked with the engineering climatology unit of the Meteorological Service of Canada to update those design values. We projected changes to design values under future climate change conditions, and we did that jointly with the Climate Research Division of Environment Canada and the NRC. And we developed a mapping tool for the presentation of design values that's appropriate to extremes and appropriate to a country with generally sparse data coverage. So if you look in the back of the National Building Code of Canada, you'll see a very large table that lists these engineering design values place by place over for about 650 locations in Canada. If you're building something for some other location, then somehow you have to interpolate between that data. And so it seemed important to build an approach for doing that. So we undertook a comprehensive update of all of the tabulated elements, primarily using the Climate Archive of Environment and Climate Change Canada, which we independently quality controlled. We developed a range of innovative data processing approaches to cope with decline in the observing network that has been taking place, and to utilize, especially for snow loads, plentiful snow depth data. There is lots of that across Canada for estimating snow loads. So snow depth doesn't tell you about snow density or snow mass. And so you need to be able to translate snow depth into snow load in an intelligent way. We made some minor adjustments to the extreme value analysis methods that are used to develop these loads. And we developed this optimal interpolation technique that I'll talk about a little bit more. So here's an example of a result, and what this shows is the 95th percentile of hourly wet bulb temperatures on the left-hand side, as developed from station data and then spatially interpolated across the country. So if you're designing a structure for a particular place, you want to know what this number is in order to manage cooling loads within the building correctly. And so you need to know that number in detail at wherever the building is going to be constructed. And so this provides a reasonable way of being able to estimate what those numbers are and to take their values into account. So with this tool that we've developed here, you can click on a particular location on the map and obtain exactly what the interpolated value is at that location. The map on the upper right shows you where the station data are, or at least the locations that are tabulated in the National Building Code of Canada, and the differences between our interpolated values and the tabulated values. And you see that there are deviations in both directions that are generally quite small. And then the panel on the lower right shows you what the value distribution is in the bottom in green across the stations that are available. In the top, what the corresponding value distribution is in a regional climate model that we use to guide the interpolation. And then in the middle, what the interpolated distribution looks like. And so you can see that the interpolation works pretty well, actually. So the placement of the contours in the map on the left was guided by output from this regional climate model. For future design values, we classified variables that are projected by global and regional climate models into three broad tiers according to the assessed confidence in the science. And so we have pretty high confidence in what we can say about how the climate will warm, so thermal aspects of climate change. But we have quite low confidence in what we can say about how atmospheric circulation, for example, will change. So the dynamic aspects of climate change. We also have much lower confidence at smaller scales. I'll be coming to that point, back to that point again. So we use output from a large ensemble of climate change simulations and use them to project changes in design values as a function of global warming level relative to the recent climate. And we did that in half-degree increments. So if you're designing a building at a particular location, what the kind of information that you would get from this is that a particular design value, like a snow load, would change by a certain fraction when temperatures are ½ degree above present, a different fraction when they're 1 degree above present, and so on. And so we did this in half-degree increments up to 3.5 degrees above present for the global mean. So these projections are given as change factors, and they're either additive or multiplicative, depending on the type of design value. And the timing of warming, which is important for using these numbers in engineering design, is determined from an ensemble of many global climate models that participated in the CMIP-5 exercise that was supported the IPCC 5th assessment, and can easily be updated using the output from climate models that are participated in CMIP-6, which is supporting the current IPCC exercise. There's a website here that gives gives access to a report that describes how these changes in design values were calculated and how the assessment was performed and so on. Okay, so here's an example of that kind of thing that was produced. And what it shows is changes in 50-year snow loads at 2 degrees additional global warming above present. And so that's something that, depending on the emission scenario, might happen during the second half of this century. And what you see, first, there's quite a lot of detail here in this projected change. You see very substantial declines in projected snow loads on the east and west coasts of this country. Also fairly large declines in southern and central Ontario, in the lee of Georgian Bay, for example. And then north of about 60 degrees north in Canada's north, in the territories, you see projected increases in snow loads. And that's all of that makes climatic sense. So including the projected increase in snow loads in the north. Well, the high north is essentially a cold desert, and one of the large-scale impacts of climate change that we expect is that there will be more moisture transport into that region as the climate warms, and therefore an increase in precipitation in that region as the climate warms. But it's nevertheless a cold area, and so most of that precipitation will arrive as snow, increasing snow loads. The mapping tool that I've been talking about uses a spatial interpolation approach that's based on kriging. Basically, we estimate design values from a large ensemble simulation of the regional climate model, and we use that as a covariate in this mapping, in this optimal interpolation approach to interpolate between design values that are estimated from stations. It's been incorporated into an online tool that you can use to look at all of the different design values that are tabulated in the National Building Code of Canada and how they might change in the future. It's still in beta at the moment, but it will. We're hoping to release it operationally within a couple of months now. Okay, so that gives you some background on the work that we undertook at PCIC. This was a 3-year project with some ongoing effort that's continuing on this tool. What I'm going to spend the rest of the time on now is a discussion of things that I've learned, questions that I've learned how to ask. The photo here is of a piece of infrastructure that is now obsolete, but a lighthouse that was built on the west coast of Vancouver Island in 1911. So it certainly has seen climate change over the period of time that it's been established there. So here's a list of concerns, and I'll talk about each of these in turn. Maybe I'll have to stop a little bit early if I run out of time. But they relate to the robustness of the supporting meteorological observing infrastructure, the robustness of the operational engineering climatology effort in Canada, and the research that needs to support it. We have a lot of infrastructure. It's actually supported by very little in terms of operational capability and research capability. There's a very large tension between the specificity of the information that's required by engineers and by the degree of scientific confidence that we can provide the community in terms of how climate might change. Design value estimation for non-stationary climates is a very large issue and a very difficult one. I've mentioned reliability targets for non-stationary climate as an issue. And I will talk a little bit, hopefully, about a uniform risk engineering design approach and what that means from a climatological perspective. So first, the hydrometeorological observing infrastructure in this country. So this is a photo taken in New Zealand of quite a rickety pedestrian bridge. It was built by the local community. Families lived on one side of this estuary. They had to send their kids to school on the other side of the estuary, and so the solution was to build this bridge, which they've maintained essentially on their own ever since, and which you can go and visit. So it's safe, but certainly not the most robust piece of infrastructure. So I use it as an analog for our in situ observing system in Canada, which is populated, not densely populated by stations, but sparsely populated by stations with uneven spatial coverage, and where the number of stations that are being maintained by the Meteorological Service of Canada is declining over time, and has been for some time. Of course, there's a lot of other data available in Canada, but it's only recently, I think, that we've been undertaking the effort that is required to be able to access that data. And so in a lot of respects, we're still very much data poor. And so the idea here is to basically to highlight that for you, and to point out that even just collecting this data and maintaining these archives and learning how to use the data that are available effectively requires careful research that's not likely to strongly impact one's H-index or generate a lot of citations. So impact is low, and so that means attracting NSERC funding and other kinds of funding is difficult. The support for engineering climatology in Canada. So this is another picture taken at the Alexandra Bridge. This is one of the anchors that retains one of the suspension cables. So this has been in service for almost a century now. This little piece of this little marvel of engineering, you might say. So as a specialty, it's currently undertaken by a very small group in the Meteorological Service of Canada with only a very little bit of research support. And within that group and more generally, the continuity of expertise is a real concern, and the thorough documentation of analysis, updating and assessment procedures is also a big issue. So when we started digging into updating the design values in the building code, we had to rely on, in some cases, information that former staffers dug out of their archives in their basements. Certainly, the documentation that was available wasn't complete to help us understand what had been done in the past. The scientific issues that this small group of people, specialists, will have to deal with are challenging. So they need to be able to do extreme value analyses with increasingly ambitious requirements. I'll be coming back to why increasingly ambitious. Non-stationarity, and evolving data sources. So if we can't continue to rely on station data, then we need to use data from other sources. And there are masses of remote sensing data and emerging high resolution reanalyses that are becoming available. But we need to understand how we can integrate this information while at the same time retaining long-term homogeneity, so that the numbers, critical numbers that we're interested in, such as how a design value is changing over time, is little or not affected by changes in the source of data that's being used. So that's an aspect that requires a lot of careful research as well. The notion of specificity versus confidence. So the photo here is taken in Shanghai in November of 2019, so not so long ago. There's a 128-story building there that I've labeled the Shanghai Tower, and it's of interest to Canadians and to Canadian engineers because it was in part designed at RWDI in Guelph in their wind tunnel, where they use analog techniques in order to study the exterior loads on buildings as a consequence of the wind pressures that they're exposed to and the turbulence that's created. So structures are built in specific places, and so local climatic details are of course very important, but confidence in what we can say about a changing climate declines really rapidly as the required specificity increases. And so it becomes really challenging for a place like downtown Shanghai and the site on which the Shanghai Tower is built. So our understanding of the physical processes that operate, physical climate processes that operate at local scales, is much lower than those that operate at larger scales, and the effective resolution of climate models is substantially lower than their nominal resolutions. So you might think that a high resolution convection permitting model with 1 kilometer or 4 kilometer spatial resolution would help you out, but the effective spatial resolution of such a model is actually substantially lower than that because of numerical constraints that have to be applied on the solutions that it develops. So the effective resolution of a model that is nominally 4 kilometer resolution is probably closer to 15 or 20 kilometers. There's more confidence in our understanding of thermal responses to the changing climate, as I've mentioned, than dynamical responses. But even surface air temperature locally can be challenging. And we learned that again this past June when a group of people analyzed the extreme heat wave that occurred in Western North America and affected British Columbia, where the highest temperatures ever recorded in Canada were recorded almost 50 degrees at one location in the Fraser Valley. And understanding the physics that produced that turned out to be and doing the extreme value analysis that was required to document how rare that event was and how its probability might change in the future turned out to be extremely challenging, in fact. There's still very little that we can say to engineers about the future intensity of extreme winds. And so that's and precipitation in local convective storms. So that remains a huge scientific challenge. And so for all of these reasons, especially regarding precipitation, the advice that's offered in Canada and also in Australia concerning extreme precipitation tends to be quite simple. And that is to rely on what's called the Clausius-Clapeyron relation applied to historical intensity, duration, frequency curves as guidance for the future. So the Clausius-Clapeyron relation tells you how water vapor content of the lower atmosphere increases as the climate warms, and it does so at roughly 7% per degree of warming. And so if there's 7% more moisture available at a particular time, then all else being equal, you might expect an intense extreme precipitation event to be 7% more intense. And so that's the simple idea behind the application of the Clausius-Clapeyron relation for the specification of extreme precipitation. So in our Design Value Explorer, that's the concept that we use. And so here's a map that shows how we think intensity, duration, frequency curves might change at 2 degrees warming, global warming above present. And so this is spatially variable because warming across the country is spatially variable. But you see that depending on where you are and whether there's more warming or less warming, intensity of the intensity of extreme precipitation as described by IDF curves would be expected to increase somewhere between 20% or up to 40% in the north, because the much more substantial warming takes place in the north. So you might ask, well, should we do this in a more complex way than by a simple temperature scaling? And we're certainly tempted to do so. There's lots of science. This is an area that's hotly debated and intensely studied. But at the moment, there's not a huge amount of we're still quite a ways away from developing a widely accepted scientific consensus on how to proceed. So we need to better understand the dependence of intensity change on the type of event, its rarity, on ambient conditions, on circulation change, on feedbacks, and so on. And as I've mentioned, there's lots of excitement about the potential use of convection permitting models. We can go to scales of a kilometer or below a kilometer. So we can go below a kilometer and have an effective scale of a kilometer. But we're really hampered by their cost and lack of model diversity in this case. Still insufficient understanding about how you nest these very high resolution regional and local climate models within global climate models in a way in which there's a good balance between the guidance that's provided by the global climate model and the driven model in the interior to produce its own useful additional information. So there's still a huge amount of research that's to be done in this area, and at the moment these tools are so expensive that it's really impossible to do a large the large body of research that is required. There's also been a body of literature that has dealt with an observational approach that tries to link changes in temperature with changes in precipitation, in the intensity of precipitation extremes via something called the binning scaling calculation. So basically, the idea is that we have temperature observations throughout the year and precipitation observations throughout the year. And so if you link how the intensity of extreme precipitation in a cold part of the year is related to the intensity of extreme precipitation in a warm part of the year, there's kind of a natural climate change experiment that's being conducted every year as you go through the annual cycle. Okay, so that's a nice idea, but unfortunately, it doesn't help you very much in projecting how warming will affect future precipitation extremes, because it confounds the effect of the annual cycle and the circulation changes that occur with the effect of warming. So there's we've published a couple of papers with Jubin Zhang and recently with a postdoc on that topic, trying to explain why this particular calculation, which I think is creating a fair bit of confusion, is not one that should be used for projecting future climate change. We still have a lot of work to do to understand how circulation affects climate change and affects changes in extreme precipitation, for example, and how that affects the changes in that might occur for events of different rarity. So this figure here shows first the two left-hand panels, upper and lower, projected changes in the intensity of 6-hour extreme precipitation events per degree of warming based on a large ensemble from a regional climate model for 2-year events in the upper panel and from 50-year events in the lower panel. And you see that there's greater intensification per degree warming for the extreme 50-year event than there is for the 2-year event. And so that's an interesting thing, that intensification is rarity dependent. When we try to unpack this a little bit and ask, well, how much is that due to the directly due to warming, or is there a relationship with circulation? And basically, what we see is that circulation, it's due to circulation, that's this change in sensitivity of the extremes to warming for rarer events comes about, at least over North America in this particular climate model, because of the effect of circulation change, as opposed to because of a direct thermodynamic impact. And so that's something that's interesting, but this is just one climate model, and so you might not want to behave to make engineering design decisions based just on exactly this one climate model. The notion of non-stationarity. So this is kind of the poster child of pictures indicating how non-stationarity might come into play in engineering design. So these are old buildings built on permafrost in Dawson City, where the fact that they were built on permafrost wasn't taken properly into account, no doubt. So we have the scientific knowledge to deal with non-stationarity, the effect of changing climate for thermal loads. So anthropogenic warming signal is discernible in observations and quantifiable, even at relatively small scales. And so we basically have the tools that we need for that. We know in principle how to deal with it for precipitation, but the signal in observations is still really only quite small and not reliably discernible. And so doing non-stationary extreme value analysis on local data is a bit of a mug's game and relatively unreliable. It turns out that you need a lot of data in order to be able to actually nail down what the effects of external forcing are on extremes, even in situations in the future climate where the signal is much stronger. And we don't know yet how to deal with this question at all for wind loads, which is, of course, a big issue. Just to give you one bit of an indication of what you can do locally or can't do locally, and why looking why it's still difficult to detect human-induced change in extreme precipitation at the local scale. So I'll offer you this particular figure from a recent paper that we published in the Journal of Climate. And what it shows is annual trends in the annual maximum one-day precipitation amount as recorded at about 7,300 stations across the globe where data are available from 1950 onwards. The blues indicate places where there's intensification. The dark blues where the increase is statistically significant. The warm colors indicate locations where there is weakening of these extremes over time, and the dark reds where those changes are significant. And so what you see is that there is, first of all, there are big gaps. So for climate research, we don't have access to this kind of data from all over the world. Sometimes it's collected in some jurisdictions and simply can't be shared. India is an example. Other places, it's simply not available. So we don't have this, you're certainly far from uniform data coverage. You do see some spatial organization in the reds and the blues, which is interesting, and you might relate that to circulation change. What you see on the right-hand side are two figures that indicate that you can see significant amounts of intensification. It's something like 9% of stations, which is bigger than substantially a larger fraction of stations than you would expect simply by random chance. With the test that was being performed, you'd expect intensification by random chance at about 2.5% of locations. So this is well beyond that. So there is something going on. But on the other hand, it tells you that if you pick a station at random in your backyard, there's less than a 1 in 10 chance that you'll see intensification at that station. On the other side of the coin, the lower right panel shows you the fraction of locations at which there is significant weakening of intense precipitation. And that number turns out to be 2.1% of stations averaged across the globe, using a test where we expect to find 2.5% of locations showing significant declines just by random chance, just due to a natural internal variability in climate system that's got nothing to do with external forcing on the climate system. So there's nothing untoward that's going on that indicates overall weakening, but the observations do indicate evidence for strengthening, but insufficient to be able to reliably know that that's the case at a particular location. And so that poses a challenge for us from an engineering perspective. So we've studied, how much data do you need in order to nail down a nonlinear, non-stationary extreme value model fitted to observational data. So you can use models climate models as a place to ask this question. Here are two examples of two runs just started from different initial conditions with the same regional climate model, where we tried to estimate basically what is the temperature scaling relationship with extreme annual maximum 12-hour precipitation is simulated from that model, from single 65-year runs representative of the current climate. And these two different realizations show two very different noisy pictures as to what the relationship is. And so the answer is you can't, within that climate model, you can't do it reliably. And to the extent that this climate model is a proxy for observations, that means you then also can't do it with observations. We can go on. This climate model was run many, many times from different initial conditions. And so you could ask, well, how much output from such a climate model would we really need in order to be able to answer this kind of question? And what approaches should we be using? And so we asked, what you could learn by doing at-site analysis, by using regional frequency analysis across small regions, what you would learn by using regional frequency analysis across much larger regions? And the answer is that you need more than 65 years of data, and you need to use a period with a much stronger signal than we see during the last half century or so, in order to be able to really nail down reliably these non-stationary extreme value models. And so it turns out you need the equivalent of many hundreds of years of data using regional frequency analysis to do this with high reliability. And so that's something that we also need to take into account when we're doing non-stationary extreme value analysis. A few quick words about future reliability. So I'm just about finished. I've got a couple more slides to go. This is a very recently built piece of road between Inuvik and Tuktoyaktuk in the Northwest Territories. It's built over top of permafrost. The way in which this is built is simply to truck dirt on top of the permafrost, a couple of meters of dirt, which hopefully is enough to prevent the exchange of heat between the atmosphere and the underlying permanently frozen ground. Whether this is a reliable approach for the future remains a question, right? And so that's why I use this particular picture in this instance. So the reliability of a structure as built won't be constant. Even under ideal circumstances, some loads will increase, others will decrease. And as I've indicated before, the probability of failure is not likely to vary monotonically. The current practice assumes constant probability of climatic load exceedance, and that's no longer appropriate in a changing climate. So the question then becomes, well, what targets should we design for? Do you design for an initial probability of failure set substantially lower than today's target, hoping that that's going to be adequate throughout the service life of the building? Do you design for the average probability of failure over the service life of the building? And if you do that, then you'd be very happy to occupy the building at the beginning of its service life, but you might not be so happy to occupy it at the end of its service life when probability of failure is higher. Or do you design for the end of service life probability of failure, which could engender very large costs in building design? So questions are, well, can you design in such a way that routine periodic maintenance and refresh might be able to maintain a given reliability target, assuming a fixed cycle, 20-year cycle or something like that, and only marginally different costs? Does one approach such and how do you approach the issue of setting reliability targets and socializing those in such a way that's acceptable across both the engineering and user communities? But I don't have answers to these questions. These are questions that are really outside my domain of expertise, but they're questions that arise when you start thinking about this. And finally, a couple of words about uniform risk versus uniform hazard. So the ASCE 7 now requires wind load estimates for return periods of between 700 and 3,000 years, depending on the structure type. And so it adopts a uniform risk engineering design approach, but it then requires these return level estimates for very long return periods. And so that, I have to contrast that with the kind of wind speed data that's available. So it's very scarce in Canada. The available instruments cover relatively short periods of record. We might be lucky if they're 50 years of record in a given location. And the records that are available are almost surely inhomogeneous as the wind instruments change over time. And so how do we go about trying to make sense of the information that we have and then extending it very deep into the tail? We'll have to use methods that seem rational, considering mixed wind climate, storm transposition approaches, and so on, that are of unknown reliability and have limited theoretical support. And so I'm going to skip over these slides. We've been trying to address some of these questions and have some suggestions, but it's an issue that I think we need to be thinking about quite deeply as we make the transition between these two types of engineering approaches. So then finally, who needs to be concerned and involved? So of course, meteorologists need to be involved, operational people need to be involved. The challenges are both operational and scientific, multidisciplinary, with different languages and cultures and different ways of organizing and regulating professional practice and different reward structures. So climate scientists, when aren't routinely asked to sign off on their work the way in which engineers are, but we are certainly held to account in other ways, such as by the IPCC process, which has a very intense approach to reviewing its reports. So those are probably the most thoroughly reviewed reports in the world, bar none. So that's it. It's been a very quick survey. I appreciate your attention and very much appreciate the very large audience that has joined us here. I've left a few URLs here, so you can find a copy of the slides on a public HTML page that I maintain. And you might be interested in the upcoming meeting of the Canadian Meteorological and Oceanographic Society meeting, where we're taking quite a service-oriented and applied approach in this meeting. So there may be things that engineers and others are interested in at that meeting. So thanks very much for your attention, and thank you, Reza.
Thank you very much, Dr. Zwiers, for this very informative presentation. Before getting to the Q&A session, I just want to mention that students who have class starting at 2:30, or they have other commitments, they can leave the seminar. We won't take attendance onwards. And as usual, you're all welcome to either post your questions on the chat window or just go ahead and ask by unmuting yourself. So I'm just going to start with a couple of questions. So, Dr. Zwiers, you mentioned that that's what I think understood, that the CC relationship is recommended for regional projections of precipitation extremes. I'm just wondering how reliable, based on the literature and your works, you think this relationship is for events like atmospheric rivers that recently we had the BC flooding that was attributed to AR, as well as the hurricanes that we hear a lot about. Hurricane seasons in these years, many hurricanes occur. So is the CC relationship applicable for these kinds of events too, or there are some uncertainties related?
So there are lots of uncertainties. So dynamical processes certainly have a big role to play. So for atmospheric rivers, for example, the kinds of questions are first whether a given atmospheric river will transport more moisture to the place where precipitation occurs in the warmer climate than it did in a cooler climate. And so that question you might be able to answer using the Clausius-Clapeyron relation. If the atmospheric river is drawing from warmer air that contains 7% more moisture per degree of warming, then you might expect it to deliver proportionally that much more moisture to a given location. But other questions that you might ask are, whether or not the frequency of atmospheric river occurrence is affected by warming. And that's a complex question because atmospheric rivers are defined relative to fixed moisture transport thresholds. So the amount of moisture that's being transported by a particular kind of atmospheric flow exceeds a certain number, then we call it an atmospheric river. We don't adjust that number for the future. But the weaker circulations in the future may be carrying enough moisture to meet that threshold. And so we would be recording more atmospheric rivers in the future. And we would correspondingly expect more events to produce atmospheric river related impacts because those impacts, the stream flows that are produced, the damage that is produced to the stream crossing infrastructure, for example, occurs as a consequence of the exceedance of fixed absolute loads, not changes in relative loads. And so I think there's a dynamical aspect to this question that that goes beyond the simple Clausius-Clapeyron question. That's for sure. So this is only very rough guidance, and it might be suitable guidance for estimating 20-year or 50-year extreme precipitation event. But the deeper that you go into the tail of the extreme value distribution, if you wanted to know about a 1,000 or 2,000 year event, if you're designing a spillway, for example, or a reservoir, then I think you need to be thinking much more deeply about the rare and unusual events that produce extremes of that kind. And they might not lie on a simple extreme value distribution curve.
Okay, thank you very much. So the other question is maybe mostly more has an engineering perspective, that climate scientists provide basically distributions of changes, and that's what's typically referred to as the uncertainty within those projections or estimations. And there is a tendency to take the mean or median of that distribution and use it for risk analysis or design purposes. However, the recent events show that typically the kind of extreme events we deal with that have more impacts, drastic impacts, are the ones that are kind of down in the tail of that distribution, further down actually, that if we want to consider those for our infrastructure design, for example, the project would be quite costly and it's hard to justify it. So I think these are two basically contrasting perspectives. One would save some money and it's considered as reliable because we are taking the average of multiple scenarios. But the other one might be safer, and maybe cost-wise, it will be more beneficial in the future. But there's uncertainty. We never know if such an event will eventually occur or not. How do you think we should approach this kind of estimation and this kind of distributions and use the values for engineering design purposes?
So this is a really hard question, of course, Reza. So, but let me start by talking about three principal sources of uncertainty. So one is just the natural internal variability of the climate system, and so that's something that's irreducible. something that we're exposed to constantly in the observed climate system. And it's also an aspect of variability that typically climate models simulate pretty well, at least at large scales. So it's a source of uncertainty that is quantifiable. And by running our climate models more, we can do a better job or running them at finer scales, we can do a better job of quantifying uncertainty due to these natural and internal processes of the climate system, the things that produce weather, the El Nino, that kind of thing. So I think that's something that ultimately we know how to deal with in engineering design, because we have a responsibility to make sure that the buildings are reliable in the face of natural internal variability of the climate system, in the face of the weather. And so that obligates you to choose a point in the far upper tail of the distribution of the weather, in essence, and or what the weather in the future might look like. So another source of uncertainty is emissions scenario uncertainty, and that's not something that climate scientists can tell you about. But that source of uncertainty becomes large as you move towards the end of the 21st century, for example. So which pathway we choose to be on, whether or not we choose to mitigate it aggressively and maintain global mean temperatures to below 2 degrees above pre-industrial, or whether or not we allow an emissions pathway at which we might go to levels of warming of 4 degrees or more above pre-industrial. So that's not something that maybe an economist can tell you something about where we are in terms of quantifying scenario uncertainty, but it's not something that climate scientists can tell you about. So in that case, an engineer would have to make a judgment about what kind of future climate they were designing for. And so one way to do that might be to think about designing for a climate that is, say, 3 degrees warmer than the pre-industrial climate. And then thinking about what that means in terms of when that level of warming might be attained as a function of which emission scenario you're on. And if you think about it in that particular way, then you would learn that if you design for 3 degrees above pre-industrial, then structure might well still be adapted to the climate of 2100 under an emission scenario such as SSP 7 or SSP 4.5, and that it might need adaptation to the climate by, say, 27 if we ended up on the pathway SSP 8.5. So you could design in such a way that you meet conditions that you judge to be plausible for the end of the 20th century, with some allowance that maybe the building will need to be adapted a little bit earlier. Okay, so that would be one approach to dealing with scenario uncertainty. And the third source of uncertainty, which we also don't know how to quantify, is climate model uncertainty. So the structural uncertainty that comes about because different climate modeling groups implement their climate models in different ways. And that leads to different sensitivities and different responses to the same forcing. So this is an uncertainty that we don't know how to quantify because we have a sample of climate models that have been run for CMIP 5 or for CMIP 6, but we don't know how the sample has been drawn. And because that makes it difficult to model that variation between climate models statistically, or to quantify really what that variation is, because we haven't sampled from the population of all possible representations of the climate system in a systematic way. On the other hand, while this uncertainty isn't quantifiable, it is an uncertainty that is reducible through further investments in climate research and further improvements in climate modeling. So while it's hard to advise the engineering community today on what an upper boundary on that particular uncertainty might be for year 2100, I think we would be able to assure the climate modeling group, the engineering community, that if we advance 10 years further or 15 years further, we might be able to be more confident in identifying which representations of the climate system are better representations. So it's currently a very active area of research, is to search for what are called emergent constraints, which give us information about how performance of climate models in the present climate tells us how they will perform in the future climate. So for that one, I think there's hope. So it's a long, complicated answer, but there are really three components to think about.
Okay. Well, it's interesting to distinguish between these sources and what should be our approach for each one of those. Great, thank you. So questions from audience. So as you can see on the chat window, Farshad is asking, I'm just wondering why the base time has been considered as 1986 to 2016 regarding the global mean temperature increase.
Okay, so this refers to this is a decision that we took in developing our design value explorer, and the reason why we used a recent 3-decade period, as recent as possible, is that the way in what we're advising the engineering community to do is to apply change factors to the updated historical design value estimates that we produced. And those historical design value estimates are representative of the recent climate. They're not representative of the pre-industrial climate. So it seemed easier to us to reference future climate relative to about the same period that the design values represent, that are available in the National Building Code of Canada, or will be available in the code.
Thank you very much. Other questions? All right, so I'm going to ask another one, if you don't mind. So I've seen in in some reports or references that people talk about the climate system reaching a tipping point. You talked about 1 degree, 2 degree, 3 degree warming periods. And can you please elaborate a bit what that really means and what are the implications of this tipping point for the reliability of our infrastructure systems, and if there's any information, or isn't that still an open question? If you can maybe elaborate on it.
Yeah, I'll try. So the notion of tipping points really has to do with the climate system as a whole, as opposed to local variability in the local, or change in local climate that we might experience in Canada. And so a couple of examples of tipping, or 3 examples that I might think of for tipping points. So one would be collapse of the Thermohaline circulation in the North Atlantic. So the Gulf Stream is part of that Thermohaline circulation. And what that does is it transports warm water from tropical regions into the high northern latitudes, the water cools in the high northern latitudes, and so it yields heat to the atmosphere. That's part of what keeps Western Europe warm, for example, and also part of what would keep Western North America, British Columbia warm. That cooled water sinks and returns to the south along basically at depth along the bottom of the ocean. And so that's called the thermohaline circulation. The word haline refers to the fact that the cold water that sinks is also dense and salty. And so the density and temperature together drive that circulation. So there's, if the thermohaline circulation collapses, then there's a change in the way heat is transported from the tropics to extratropical areas, and that could have a substantial effect on the climate that we experience in mid-latitudes. So we really don't know a lot about the probability of thermohaline circulation collapse. But, another possible tipping point might be much more rapid melting of the large ice sheets than we've been observing and that our climate models take into account. And so that would also have an impact on the thermohaline circulation, but it would lead to rapid sea level rise, affecting coastal communities and coastal engineering infrastructure and so on. A third type of example might be rapid release of the carbon that is bound up in the permafrost. So the permafrost contains a great deal of stored carbon, and as the permafrost melts, that organic material that is stored in the frozen ground begins to thaw and decay, and so then there's rapid release of carbon dioxide into the atmosphere, and so that might produce an accelerated warming as time goes along, a positive feedback on the warming process. So none of these things are taken into account in current climate change projections. Not all would have a substantial impact on Canadian climate. They would certainly have a very substantial impact on the global climate system. So it's really hard to assign probabilities to these rare, possibly low probability outcomes. So if you're designing a house or a subdivision, maybe you might not think about it very much. If you're designing a hospital in a low-lying area, then maybe you do have to think about the possibility of sea level rise and the implications that might have for its reliability.
Okay. Excellent. Thanks. All right. We're well beyond our allocated 1 hour time. I just want to thank again Dr. Francis Zwiers for accepting this invitation to give this very interesting talk. So there has been a lot going on at PCIC, obviously, since I left. So I really hope that you will also agree to join us, hopefully in pretty soon, in person, to also visit our campus as well. Thank you again for your time, and I really appreciate that.
Yeah, thanks very much, Teresa, and thanks everybody for your attention and interest.
Thank you. Thank you all, and I'll see you next week. Have a great day.
Bye.